Hi everyone. In this lecture, I will be talking to you about how to use Bayes' theorem to solve questions where you are given multiple pieces of evidence. So in this first video, I will talk about how to solve those kinds of problems where we assume that the pieces of evidence are independent. And when we make that assumption, we will see that uh, there's a simple way of solving the questions. But in general, we can't assume that the evidence that we're given is independent. So in the next video, I will talk about how to solve questions where the pieces of evidence are not independent. And finally, at the end of the second video of this lecture, I will also talk about how to use something called the conditional rule of total probability in order to make predictions about future evidence given multiple pieces of earlier evidence. So let's get started. When I introduced Bayes' theorem in the previous lecture last week, we are asking about the probability of certain hypotheses given certain pieces of evidence. So for instance, if you don't know the exact composition of the urn which you're drawing from, you can ask, what is the probability that the urn that I'm drawing from is type 1, say, given that I've drawn a black ball? But we can also ask about the probability of the urn being type 1 or of any other hypothesis given multiple pieces of evidence. So for instance, if the first draw is black and the second is white, say. So the motivation for the multiple conditions we're talking about in this lecture is that sometimes you get two new pieces of evidence or information instead of just one, and you're interested in what the probability or the conditional probability of a hypothesis is given those two pieces of information. And this lecture will be telling you how to use Bayes' theorem to answer this question. So let's return to an example which was given in the previous lecture. So in the previous lecture where I introduced Bayes' theorem, we had a case where a cab was involved in a hit and run accident at night. And we know certain information about what the possible cabs are that are in the city, and we also have some information about a witness. So in the cab case for the previous lecture, we knew that 85% of the cabs in the city are green and 15% are blue. And furthermore, we said that there was only one witness. So in the previous lecture, when we talked about this cab case, we said that one witness came forward. And the one witness who came forward is 80% reliable at telling the color of a cab if they see them. And this witness said that the cab was a blue one. Okay, so here W1 means that the witness 1 said that the cab was blue. So we could ask, as we did in the previous lecture, what's the probability that the cab was in fact a blue one, which committed the hit and run, given just that one witness said the cab was blue. But now we ask about a more complex probability. Now let's suppose that instead of just one witness coming forward and saying the cab was blue, suppose that in addition another witness also was at the scene of the crime and says that the cab was blue. And now let's assume that this witness has the same amount of reliability as a first witness. So both witnesses are 80% reliable. And so given the testimony of the two witnesses saying that the cab was blue, we can ask, what is the probability that it was blue given that the first witness says it's blue and the second witness says it's blue? That is, what is the probability of this hypothesis that the cab was in fact blue, given these two pieces of evidence from these two witnesses? And now let's use Bayes' theorem to calculate this probability. So here's how we solve the problem. First, we simply apply Bayes' theorem, which tells us that the probability of the cab being blue, given that the two witnesses says it is, equals the probability that the cab was blue unconditionally of any witnesses. That is to say that there we're concerned with the background or base rate probability that it might have been a blue one versus a green one. And since in this setup there's 15% of the cabs in the city are blue and the other 85% are green, that means that the probability, the base rate or the unconditional probability before we have any other evidence that the cab was blue is going to be 15%. Okay, so we need to know the base rate or the background probability in the claim that the cab was a blue one. But we also have to know the probability of the witnesses saying that it's blue, given that it was blue. So we have to think about the reliability of the witnesses. And then furthermore, we have on the bottom of this fraction, we have to think about the unconditional probability of the witnesses saying it was blue. So we have to think about what are the possible ways that the witnesses might actually say it's blue when it's not. And we'll see that when we unpack this using the law of total probability. So as I just mentioned, we already have one of the terms. We know that the background or unconditional probability that it was a blue cab is 15 out of 100 because 15% of the cabs roaming around the city at night are blue. And also, we're going to assume that the two witnesses are honestly reporting what they each saw. That is to say that, given that the cab was blue, the witnesses are not influencing each other's testimony. Both of the witnesses are honestly reporting what they saw. And what that means is that, given that it was blue, the probability of both the witnesses saying that it was is just the exact same as the probability of the first witness saying it was blue times the probability of the second witness saying it was blue. Now, I'm going to come back to this assumption in the context of questions about urns, where hopefully this will become even more clear. But in any case, given this assumption that the testimony of the witnesses is independent, given the fact that it was blue, we know that the probability of this the probability of the conjunction of W1 and W2 given B equals the probability of W1 given B times the probability of W2 given B. And since the witnesses are 80% reliable, that is just 80 over 100 times 80 over 100. So that means that so far from the question, we know the numerator. But now we have to think about the denominator, for which we apply the law of total probability. And so we apply the law of total probability, which tells us that the probability, the unconditional probability of the evidence of the witnesses saying it was blue equals the probability of them saying it was blue, given that it was blue, times the unconditional probability of it being blue. And then we add the conditional probability of the witnesses saying it was, given that it's not blue, times the unconditional probability that it's not blue. So we consider not just the case where the cab was blue, but we also have to think about the reliability of the witnesses in the case where the hypothesis under consideration is false. And from the question, we know that, so again, since we're assuming that the witnesses are independent, given the facts, we can reduce this conditional probability to the probability of W1 given not B times the probability of W2 given not B, which we know from the question is 20 over 100 times 20 over 100. And then we know that the probability of it not being a blue cab as background is 85 over 100 because only 15% of the cabs in the city are blue and the other 85% are green. So from the question, we know how to calculate the denominator. And so we just simplify this and we get that it's 13 out of over 100. So now we can simply finish the calculation. So in the previous lecture, where we simply calculated the probability that the cab was blue, given just one witness coming forward and saying it was, what we got was that probability was about 41%. Now here, the number we get for the probability that the cab was in fact blue if there were 2 witnesses, is 96 over 130, and that's a bit over 50%. So this makes sense in that the probability of our hypothesis that the cab was blue, given an additional piece of evidence supporting that, increases that probability. But what I want you to note as we move forward is that in solving this question, we made a crucial assumption in order to simplify the conditional probability of the witnesses saying it was blue, given that it was in fact blue, or given that it was in fact not blue. And what we did was we applied a conditional rule of multiplication on the assumption that the witnesses were independent. The testimony of the witnesses, was independent given the facts. And that's how we were able to calculate these conditional probabilities by simply considering the probability of each witness given B, or each witness independently given not B. So now I want to think a bit more about that assumption, and this is the crucial assumption which we've made in solving this question. So we made the assumption that the witnesses were separately reporting what they honestly thought they saw. So this assumption that the witnesses were not in cahoots gave us that the probability of both witnesses saying it was blue, given that it was, equals the probability that the first says it's blue, given that it was, times the probability that the second says it's blue, given that it was. And I want you to note one thing, which is that this assumption is not the same as saying that W1 and B are independent, and W2 and B are independent, and W1 and W2 are independent. So when we're assuming that the witnesses are not in cahoots, we're not assuming that each of these three propositions are independent of each other. So for instance, the witness saying that it was blue is not independent of it being blue. In fact, since the witness is very reliable, and to be precise in this example, the witness is 80% reliable, whether the witness says it's blue actually does depend very much on whether it is blue. And furthermore, and this is slightly more complex, W1 and W2 aren't independent of one another in an unconditional sense. And that is because if the first witness said the cab was blue, then the chance that it was blue increases. And that itself makes it more likely that the second witness will say it's blue as well. So when we're assuming that the witnesses are honestly reporting what they saw and they're not in cahoots in any way, what we're assuming is that conditional on B, W1 and W2 are independent. And that allows us to calculate their conjunction conditional on B by simply multiplying their individual probabilities conditional on B. But that assumption is not an assumption that W1 and W2 are unconditionally independent. And it also is not the assumption that W1, for instance, is independent of B. So just to reiterate, the crucial assumption is that the witnesses' reports are independent, given that the cab was in fact blue. And in order to make this more clear, you should think of the testimony of the witnesses like two draws from an urn, where after each draw, you replace the marble you've drawn and then shake everything up. So what that means is that given a specific composition of the urn, so suppose that we're only considering black and white marbles, right? Supposing that there's a specific composition, say 50% black marbles and 50% white marbles, each draw you make from the urn over and over, so as long as you're replacing the draw each time, each draw is independent of the previous ones. So the probability of your drawing black versus a white is going to be 50-50 each time, because each time you put back what you've drawn into the urn. So that is to say that given a specific composition of the urn, each draw is independent of the previous ones, and that is exactly the assumption or a similar assumption that we're making when we say that the witnesses' reports are independent, given that the cab was in fact blue. So I will return to this point and make it more precise in a formal way after discussing how to solve a case where we cannot make this assumption that the evidence or the samples are independent given the hypothesis.